The first two industrial revolutions scaled raw physical productivity. Steam power and the electrical grid gave factories mechanical force to run mass assembly lines. Industry 3.0 transitioned to computation. Early digital systems and electronics allowed engineers to automate basic logic and repetitive workflows. By Industry 4.0, cyber-physical systems pushed automation to its peak, often with the intent of engineering human operators out of the loop entirely. Industry 5.0 marks a deliberate turn back toward the worker. This model integrates collaborative robots, or cobots, to work alongside humans, prioritizing well-being and man-machine cooperation over total isolation. By utilizing human judgment to optimize resource-heavy processes, this model targets energy efficiency and waste reduction targets set by the UN Sustainable Development Goals. The World Economic Forum's 2026 Future Jobs Report tracks the impact of this transition on the global labor market. This data indicates that by 2030, extreme technological automation will displace 92 million routine jobs worldwide. However, the same technological shift will generate 170 million new roles, resulting in a net creation of 78 million jobs. Understanding why advancing technology requires an influx of more human workers requires a first principles deconstruction of the Industry 5.0 hardware and network stack. Every macroeconomic shift in the system originates at the microscopic level, deep inside semiconductor fabrication facilities. Chip manufacturing has entered the Angstrom era. Fabricators are now mass-producing 2-nanometer gate-all-around transistors, a multi-sided architecture required to process massive AI workloads without overheating the silicon. Shrinking components to this extreme density introduces severe side-channel vulnerabilities, meaning security must be hard-coded into the silicon itself. Engineers deploy zero-trust system-on-chip designs. Using open-source tools like OpenRoad, they build isolated hardware blocks that actively shut down unauthorized intrusion pathways at the root level. Silicon fabrication generates a heavy carbon footprint, creating a tension between computational power and environmental goals. Manufacturers are responding with decarbonized wafer production, transitioning to low-temperature solders and dry etching processes to cut energy consumption and chemical waste. These 2-nanometer chips generate secure, sustainable processing power. Yet, without a dedicated ultra-fast network to deploy it, that computation remains localized. Look at a modern autonomous port. Moving thousands of heavy transport vehicles simultaneously requires constant wireless synchronization. Standard wireless infrastructure cannot handle this volume of data without critical delays. These facilities rely on 5G advanced networks, designed specifically for autonomous industrial control. This network architecture, control and user plane separation, decouples central cloud logic from data transmission pathways. By pushing the user plane function out of centralized servers and closer to the factory floor, the network reduces signal travel time to less than 10 milliseconds. That sub-10 millisecond speed enables edge computing. Instead of relying on a distant cloud, machines use local microprocessors to run compact machine learning models called TinyML. This localized AI inference allows robotic systems to visually process their environment and react to complex physical variables instantly, without waiting for external server authorization. Ultra-low latency edge networks serve as the connective tissue, allowing individual physical machines to synchronize and operate as a unified digital ecosystem. When you map that entire digital ecosystem into a dynamic 3D simulation, you get a digital twin, a virtual model synchronized in real time with a physical logistics hub or city grid. The accuracy of these simulations depend on intelligent sensor arrays. Networks of LiDAR and optical cameras act as the primary eyes, streaming continuous physical data into the virtual model. The application of this edge processing and AI extends into specialized fields like medical informatics. Hospitals are deploying ambient clinical documentation AI. These systems use speech recognition to listen to the dialogue between a clinician and a patient, then automatically map that conversation into standard ICD-10 medical codes. This workflow reduces a physician's manual charting time by up to 15.6 hours per week, directly lowering clinical burnout rates. However, ingesting streams of clinical data from thousands of dispersed edge sensors creates vulnerabilities regarding data integrity. To secure the inputs, engineers use blockchain technology. By providing a decentralized, tamper-proof ledger, the blockchain ensures the cryptographic integrity of the data before the AI analyzes it. While AI handles documentation and blockchain secures data, reconciling these multi-sector inputs into high-level policy or emergency response requires qualitative human reasoning. This oversight is the core of the new model. It leverages intense automation to elevate the human worker into the role of a systems orchestrator. Through collaborative robotics, or cobotics, highly responsive machines integrate safely alongside human professionals in a shared physical workspace. Returning to the World Economic Forum data, the numbers align. The 92 million jobs being displaced are those dedicated purely to routine physical execution. The 170 million newly created roles demand different competencies. The labor market is seeing explosive demand for AI specialists, big data experts, and cybersecurity engineers required to architect these networks. The technological skills required to participate have evolved. Basic computer literacy is being replaced by applied skills in AI prompt engineering and cloud system management. Beyond technical ability, cognitive skills are paramount. Operating a massive digital twin requires analytical thinking and the flexibility to manage complex, overlapping systems. Finally, the unautomatable human skills remain critical. Whether navigating patient care alongside clinical AI or directing cobots on a manufacturing floor, emotional intelligence and interpersonal communication must converge with technical expertise. The global workforce is not locked in a competition with robotics. Industry 5.0 represents the convergence of extreme technological capability and indispensable human oversight.